Okay, so first of all, I would like to thank the organizers. I'm really enjoying this program, and it's a real pleasure to talk to you about this subject, which is actually one of the main topics of my PhD thesis. So it will be about a family of SDEs, Bessel processes, which are well-known diffusions, and then more recent a family of processes which are actually correspond to SPDEs. And it turns out that in a certain regime, these equations involve a kind of renormalization, which may appear trivial in some sense, but which is interesting in the way that this renormalization acts on very unusual functions, which are local times. Okay. So here is the plan of my talk. So the original motivation is to model the random evolution of a continuous interface over an obstacle. So at equilibrium, we can model such an interface by probability law, which could be the law of a Bessel bridge. I will define it later on. And the dynamics can be modeled by an SPDE that Lorenzo and I call Bessel SPDE. And these equations, in a certain regime, involve a renormalization of local times. And I forgot to mention, of course, this is based on joint work with Lorenzo Zambotti, my supervisor. So I will start by introducing Bessel processes. So this is a very standard definition. So the way we define it is by first introducing squared Bessel processes. So namely, for any parameter delta, which is a non-negative number, and for any y, which will be the initial condition, we can look at the following stochastic differential equation. So it's just it's a nice SDE with a drift, which is just given by delta, which is a deterministic slope. And there's a diffusion coefficient, which is given by square root of y. So there is a theorem in stochastic analysis called Yamada-Watanabe's theorem, which ensures that such an equation has a unique strong solution. And you can check, moreover, that this solution is non-negative, so that the absolute value of y is equal to y, and you can just write y inside the diffusion coefficient there. So this is what we call, what is called a squared Bessel process of dimension delta. Why we call delta a dimension will appear later on. So these are very nice processes. In particular, we can compute many quantities related to these processes very explicitly. For example, we can compute their transition densities, and these involve some Bessel functions, hence the name. So a remark that will be important for us is that you see that the bigger delta, the bigger y the squared Bessel process will be. In particular, if delta is big, y will not visit zero very often. On the other hand, if delta is small, this process will visit zero a lot of time, and there will be very phenomena arising there. Okay, but the processes we're interested in are Bessel processes, and these are defined as the square root of the previous processes. So namely, you set small x to be the square root of small y, and you define xt to be the square root of yt. So this is a continuous Markov process on R plus that we call the delta dimensional Bessel process started from x. So these are very nice processes. They have remarkable properties. So one of them is their scaling. So they scale like Brown motion, namely for any lambda, x of lambda t is equal in law to square root of lambda xt as a process. And moreover, these Bessel processes arise as scaling limits of various discrete models. So for example, they arise as scaling limits of pinning models. Yeah, they appear in various contexts. And there are, for example, two specific ways of constructing a Bessel process, starting from Brown motion. So for example, if you start from Brown motion, you can look at xt, which is the absolute value of bt. Then you obtain a process whose law, you can check, is equal to the law of a one-dimensional Bessel process. Okay, and you can do also something else. If you have Brown motion, you can instead look at the law of the Brown motion on the interval 0, 1, conditioned to remain non-negative. This is a singular conditioning, but there is a sense to give, the way to give a sense to this and then you obtain a probability law, which is equivalent to the law of the three-dimensional Bessel process on 0, 1. Okay? And actually, you can do other things. So more generally, to generalize the first point, if you take any integer d, and you take a d-dimensional Brown motion, then the Euclidean norm of this Brown motion is a d-dimensional Bessel process. That's the reason of the name dimension for this parameter delta. So here, for example, if you look at the two examples that I mentioned here, they have very different behaviors with 0. So we just draw a picture. So if we take delta equal to 3, we have this process here. So roughly, we do, so if it starts from 0, we do something like this. But it will not visit 0 between 0 and 1. And if we look, on the other hand, at the one Bessel process, we'll have something which rather will look like this. So this is so equal not to a reflected Brown motion, and it will actually visit 0 an infinite number of times. And so, actually, what is nice with Bessel processes is that very generally we can give a very precise notion of to the notion of how much time does the process spend at a given level. For example, at the level 0. And this is done via the notion of local time, to which I'm going to switch now. So. More generally, given non-negative number b, we can ask the following. How much time does a delta-dimensional Bessel process spend at the level b? And there is a very precise way of answering to this. Namely, you have this proposition. So there exists a continuous process of two variables, b and t, such that almost surely the following holds. For any non-negative function on R plus, f, you can rewrite the integral from 0 to t of f of x as the integral over all possible values of b that the process will take of f of b times this number here, which quantifies the time spent by the Bessel process at level b between 0 and t. So this is b to the delta minus 1 times a factor which is precisely this local time. So here you see there's this measure b to the power delta minus 1 dB that appears. The reason why it appears is that this is a reversible measure for the Bessel process. And actually it will also play a specific role later on. So in particular, one can ask, for example, what will this quantity be equal to when b equal to 0? So in other words, when does the Bessel process visit 0? And the answer is as follows. So if you denote by z of x the contact set, so the set of times where the process xt vanishes, then you have the following dichotomy. If the dimension is bigger than 2, then the contact set is empty almost surely. You don't visit 0. Whereas if the dimension is strictly smaller than 2, then this contact set is infinite almost surely. And actually, you can say much more things. You can, for example, compute the Hausdorff dimension of this set explicitly. So in particular, in this dichotomy, we recover this picture here. Okay, now something that might puzzle you is that how we introduce Bessel processes is in an indirect way. We first define squared Bessel processes as the solution of some SD, and then we took the square root. But of course, why couldn't we just define Bessel processes as the solution of some SDE? Well, actually, we can do that. We just apply Ito's lemma, which we can do at least when the process x does not visit 0 too much. And we obtain the following. So I will write it down because I will need it later. So when the dimension is big enough, so for example, bigger than 1, you find that the following holds. Just by applying Ito's lemma, you have the SDE satisfied by a delta Bessel process of dimension bigger than 1 is given by this SDE over here. So you have additive ground motion, and you have a singular drift, which is 1 over x, times some constant which is strictly positive, because delta is bigger than 1. Now, what happens when delta is equal to 1? So here, this quantity, this constant here, will go to 0. But on the other hand, this integral here, because x will visit 0 more and more, this integral will actually diverge. So here you attain a multiplication of 0 times infinity. And actually, you obtain here in the limit something which is non-trivial, namely, you have a local time over here. So here, this will become 1/2 local time at 0 plus bt. So this is the general term is supported only on the points where x vanishes. This is actually the SD of the reflecting Brownian motion. Okay, now what happens when delta is smaller than 1? Well, we would be tempted to just reuse this equation here. So we would like to write bt. And then we would like to rewrite this quantity here. But the problem, as I hinted to you before, is that this will be diverging. When delta is smaller than 1, this process will visit 0 very often, and this will be an infinite quantity. So the question is, by how much is it infinite? And to give an answer to this question, we use the local times. So by the formula that I showed you before...
Also shift the blackboard up.
Yeah, sure. So the opposite effect. We have to find the critical height. Okay. So here, using the occupation times formula that I showed you before, this you can rewrite as the integral from 0 to infinity of 1 over a times LAT, and then there's a delta minus 1 dA. So here you see there will be a problem because at 0, this quantity is non-zero, and here you will have a to the power delta minus 2. And since delta is more than 1, this will not be integrable at 0. So how to cure this divergency? Well, you do something very naive. You just force this to vanish at 0 by subtracting its value at 0. So here, you can just try to do that, and it turns out that if you do this trick, this integral here is actually convergent. The reason is that L has some continuity, some Holder continuity property, which ensures that close to 0, this will give a bound which is integrable. And actually, not only that, you also have this equality. You have this SD. So this is something which is not trivial at all, and actually you prove it a posteriori. So just a second. Yeah.
So you subtract, but you don't compensate for this subtraction.
You don't need to. So yeah, this is something surprising. So you see this term, it's difficult to understand what it means. So maybe I will appear in my slide. So in some sense, this term is not always repulsive. So sometimes it's repulsive, sometimes it's attractive, according to if L0T is smaller or bigger than LBT. But I don't have a very good intuition of what's going on here. So as I told you before, so these two SDEs are very nice. You can define Bessel processes of dimension bigger than 1 as the solutions to these equations. For example, for this, you just use Korokal problem. But for delta between 0 and 1, Lorenzo and I have never seen a definition of XD as the unique process solving this equation. So in this case, it's not a problem because you can always take the square, and the square satisfies the squared Bessel process SDE, and that's fine. But in the case of SPDE, that's a problem because when you have SPDE, it's bad to take the square because you obtain even worse SPDEs. Okay, so that was for the SDEs. Now I will switch to the world of SPDEs, but before that I will just introduce a definition, which is the definition of Bessel bridges. So what is a Bessel bridge? So if you take xt to be a delta dimensional Bessel process starting from 0, you can look at the same process but conditioned to hitting 0 at time 1. Then this probability, this conditional law is known as the law of a delta dimensional Bessel bridge from 0 to 0 on the unit interval. So, for example, going back to the examples here. So in the cases delta equal to 3, you will have something like this. And this is actually equal in law to the Brown excursion. So a three-dimensional Bessel bridge is equal in law to a Brown excursion, while here you will obtain, okay, something like this. I didn't draw very well. And this is a reflected Brown bridge. Okay, these two processes will pop up in principle. So. Okay, now think of these laws as fixed probability laws on the set of continuous functions, and now our goal is to define SPDEs that have these measures as invariant measures. So this idea started in the 2000s when Lorenzo introduced a family of parabolic SPDEs which have properties analogous to Bessel processes and that have Bessel bridges of dimension bigger than 3 as reversible measure. So the story starts as follows. So in 1992, Nuala and Pardue introduced and solved the following equation, which is a stochastic heat equation with reflection on R plus times the unit interval. So what is it? It's a stochastic heat equation. Here psi is space-time white noise. And you add a random measure eta, which is actually an unknown. So here the unknown is the couple u eta solving this. And eta will be supported on the space-time points where u vanishes, which is encoded in this requirement here. So there exists a unique solution to this SPDE. In 2001, Lorenzo proved that this SPDE has the law of a three-dimensional Bessel bridge, or a Brown excursion, as invariant measure. So that is nice. Now actually, we can ask, can we do the same for other values of delta? So for example, if you take delta bigger than 3, then you define this constant C of delta, which is a positive constant for delta bigger than 3. And you can consider this SPDE. It's a stochastic heat equation with a drift which is a repulsive drift. So it's C, a constant, over U cubed. So this SPDE turns out to have a unique non-negative solution U. And moreover, it has the law of a delta dimensional Bessel bridge as a reversible measure. So we call these SPDEs Bessel SPDEs. That's the reason for these notations here. And you see there's also a nice analogy with Bessel processes because, for example, this SPDE here is the analog of the Bessel SDE for delta bigger than 1 that was here, while this SPDE is the analog of this SD for the reflecting Brown motion. And these SPDEs are actually natural SPDEs to consider because they arise as scale limits of various discrete interface models. Moreover, they have several remarkable properties that are reminiscent of Bessel processes. So for example, they have this 1 to 4 scaling, which is the same scaling as the stochastic heat equation. And one can also describe very precisely contact set of the solution, so how many times the solution hits 0. Now, what about delta smaller than 3? This question has been open since 2001, and it is interesting particularly for the value delta equal to 1, because it is believed that the SPDE for delta equal to 1 should describe the scale limits of some dynamical critical Penning models. Lorenzo and I recently gave a partial answer by deriving integration of parts formulas for the laws of Bessel bridges of dimensions more than 3. And these formulas sort of allows us to identify what should be the correct SPDEs to consider. And so these SPDEs should have this structure with a drift here that should involve renormalized local times, in a flavor reminiscent of what happens for low-dimensional Bessel processes. More precisely, we conjecture the following. So if we look for all fixed space point x, we can look at the hypothetical solution u of t and x as a process of time, and we believe that there should exist a process albeit of x, which should be a local time for this process, and that should satisfy this occupation times formula, which is the same as the one we had for Bessel processes. So for all non-negative function on R+, the integral from 0 to t of f of u should be equal to the integral of f of b times this quantity, with, you see here, the same scaling as we had for Bessel processes. So this is a conjecture, and we also conjecture that the local times should have a vanishing first-order derivatives at b equals 0. This arises as consequences of our calculations. It's not proven, it's conjectures. Now with this, we have the following conjecture SPDEs. So for delta between 1 and 3, the drift would be given by this quantity here. So we would still have C of delta. And instead of the 1 over u cubed drift, which would be divergent in this regime, we have the same quantity but with renormalized local times. So we do the same trick as for Bessel processes. We decompose the drift using the occupation times formula. At first sight it will diverge, but we cure the divergency by subtracting to the local times the value at 0. Now, remember that I said that the local time has a vanishing first order derivative at 0. So by an easy power counting, you can check that for all delta between 1 and 3, this integral should converge. And actually, we believe that it should describe the drift. However, if we go to lower values of delta, for delta smaller than 1, the drift should have this form here, where we further subtracted the second derivative of the local time at 0. So here we have a Taylor remainders at order 2 rather than order 0 that appears. Now, the most interesting case, delta equal 1, what happens? So it turns out that it seems that the drift should be a degenerate drift, which should correspond to the second derivative at 0 of the local time. And so we would have this following SPDE. And this should describe the scaling limit of dynamical critical Penning models. Okay, so these the SPDEs that I just wrote are still essentially conjectural, but what we do have is integration of Laplace formulae for the laws of for the invariant measures. And by Dirichlet form methods, we can actually construct a weak form of the SPDE for delta equal to 1 for stationary solutions. And the case delta equal to 2 can be treated similarly. But we're still far away from really being able to solve the SPDEs that I wrote before, because they lie at the crossroads of major open questions. And one of the principal issues is the question of local times for SPDEs. So actually it's very still unknown if a large family of SPDEs do have nice local times. And as I told you before, even in the SDE case, these SDEs which involved local times as well as the solution itself seem to be very complicated. Okay, now before I finish, I would like to give an insight of what is the relation between all the SPDEs that I showed you above, because they seem quite different. Actually, they have a common feature. And indeed, we can write all the SPDs above in a unified way using a family of Schwarz distribution, mu alpha, that can be seen as fractional derivatives. So what are these? So for alpha strictly positive, you can consider the following measure on R+. So it's 1 over gamma of alpha times x to the power alpha minus 1 dx. So here we recognize up to some factor the reversible measure for the alpha dimensional Bessel process. So why do I put this 1 over gamma of alpha? It's because actually you can check that this family of measures has nice properties. So for example, it is a convolution semigroup in alpha. Now, we can extend this family of measures to a nice family of Schwarz distribution as follows. So first of all, if alpha is a non-positive integer, you just define mu alpha as follows. So for all test function phi, you define mu alpha of phi as minus 1 to the power k times the k derivative of phi at 0. So this gives you a nice Schwarz distribution. And if alpha is a negative number between two integers, then you define mu alpha as follows. So for all test function, mu alpha of phi is like the first measure, but then in order to make this integral well defined, you subtract the Taylor polynomial up to order k. And this gives you a well-defined Schwarz distribution. So actually these distributions are very classical. They arise in several different contexts. And for example, they are very similar to a notion of fractional derivative introduced by Caputo. So the reason why we can see them as fractional derivative, so I can write the formula here, is that, for example, if you take any alpha in R, and for any test function phi, you have mu alpha of phi prime, which is equal to minus mu alpha minus 1 of phi. So this is a kind of generalization of the fact that, for example, the derivative of the derivative is second derivative, right? But this extends this idea to any possible value alpha. And actually, so for example, they also arise these measures in a theorem in analysis called Ramanujan's master theorem. So Ramanujan used this theorem to prove many identities. Some of them were also false because he used it, he didn't put the correct assumptions, but it's interesting. Okay. Now,
Ramanujan had an inversion. Yeah. He never gave any conditions why they justified.
pardon?
Ramanujan didn't give any conditions for
Yes.
the inversion to be satisfied.
Yes. But I mean, he didn't, so in some,
It's just a formal formula.
yes, but in some cases you can put the correct conditions so that the formula holds. So now using these measures, these distributions of mu alpha that I introduced, you can rewrite all the equations in a unified way. So for example, the Bessel SDs can be written as follows. So for all delta positive, the drift is just the distribution mu delta minus 1 acting on the local time times some constant. Whereas, and you can do the same for the Bessel SPDEs. So for all delta positive, the SPD is just stochastic heat equation with a drift, which is given by mu delta minus 3 acting on the local time.
So mu 0 is just
The Dirac.
the identity. Yeah.
Yes, it's the Dirac at 0, exactly. So you see here, the reason why you have mu delta minus 1 here is because you had this drift in 1 over x, while here you have mu delta minus 3 because the drift was 1 over u cubed, in some sense. But these formulas work for all delta. But of course, the drawback here with this notation is that we lose a bit the sight of what is the real meaning of the drift here. If it is, for example, here, is it repulsive or is it a reflection or is it attractive? In this notation, it's a bit abstract. But
And the 3 is because the parabolic dimension of the space is 3, or?
so in the case of the SPDE, you had this drift in 1 over u cubed. And this indeed guarantees that your solution will scale like
1, 3, no, 5.
yes. So this is the drift that ensures that you have the scaling like stochastic heat equation. Okay.
Yeah, so it's related to the, because the two equations are similar only if you consider that you replace dt by the it operator. Because otherwise in the second equation you have a term more.
Mhm.
You see what I mean? I mean, they are not very, I mean, if you look like this, there is a term more in the second equation. The it operator, no? The Laplace.
I think.
In the first there is no
because
Laplace.
you want to write it in integral form. That's the point.
No, I wanted to understand why you say that they are similar.
No, I don't say that the above and the bottom are similar.
Yeah, but I'm saying maybe they are similar. On the first you have I'm trying to argue in your favor, no? In the first there is dt, and you have 1. In the second you have the it operator, and you have 3, which is the dimension
yes.
of the it operator.
Yes, it's related to the
in the
scaling.
parabolic.
Yes, sure. So, okay, so here we are very far from understanding these SPDEs, but you see there's a nice structure behind, and we think it's worth exploiting this structure, and we'd be very happy if some of you have some suggestions of because maybe some of you are I'm sure are very familiar with this standard kind of renormalization, so I would be happy to hear it. So, okay, so I will stop here. Thank you very much.
Comments or questions?
I have actually just a naive question. So, if I understand what you said correctly, you can solve the SDE, not the SPDE, for all delta positive, right?
So yeah, so you can. The problem here is delta smaller than 1, and you can do this by cheating. So how do you cheat? You say let's take a solution to this, and let's look at the square.
Oh.
And the square is
That gives you uniqueness.
Pardon?
Then you have uniqueness by
You have uniqueness
because you have it for the square.
Yes, and then you just take the square root. But the problem, as I said, is that you cannot do. I mean, you could try to do it for the SPDE, but you would obtain. If you take the square, you would obtain a kind of generalized KPZ with a.
But I mean, actually, the question that I wanted to ask is, can you, for example, consider that equation for delta less than 0, which seems like an easier step than looking at that complicated SPDE?
So you like here to look at.
And you would also have this derivative of subtraction. Does that make any sense?
I don't know. I'm not very sure because. So you can define Bessel processes of dimension as smaller than 0, but I doubt that they would satisfy such an identity. Yes, I've thought about it, but I think that the correct object, if you want to go below 0, would not correspond to some stochastic process. It would be a more exotic thing. So
Process even.
I don't think so. I don't remember it now, but I don't think you will obtain some stochastic process. For example, if you just plug here, you just take a first order Taylor remainder, and you look what happens when delta is between -1 and 0. I doubt that you will obtain sensible process, but maybe I'll have to check.
And the other question was, why does the derivative form thing only work for the dimension 1 and 2?
Oh, so the point is that if so for delta equal to 1 or 2, you can represent your Bessel process as the Euclidean overground motion. Now, and this allows you. So if you look at you want to look at this form. So here you will have, so P delta will be the law of the delta Bessel bridge for delta equal 1 or 2. So this, you have to check that this form is closable, okay? And if delta is not equal to 1 and 2, we don't even see if it's closable.
But didn't you have this integration by part formula?
It's an integration of parts formula, but the drift term is not really of the form expectation of expectation of a density times, so it's not absolutely continuous with respect to your invariant measure. It's not a measure, it's generalized functional in the sense of Schwarz.
So it doesn't even let you prove plausibility of the form.
Right, so you see, because you see these are not real drifts, so for example for the SPDs you have renormalized local times, these are not genuine drifts. And in the Dirichlet form, so for the integration parts formula, that gives you a drift which is not a real, so you have a problem.
Yeah. I have a suggestion, because now you make me think, because you wrote the equation for x equal modulus of b. If you're willing to use quantum probability, then there is discrete approximation. So you can take random walk, okay? You take the modulus of the random walk. This is quantum stochastic process, which can be described. So maybe there are some way to approximate things in the quantum world.
I think
it will never be interesting. I mean, if you take a modulus of a random walk, it's not a nice Markov process, okay? But if you're allowed to use quantum probability, then it's a Markov process.
Interesting.
Until you need to allow to use random variable which does not commute. That's the point. Okay, there you have more freedom to construct the objects.
Okay, thank you for the suggestion.
I have one small comment, which is that perhaps the subtractions that you were using to define the fractional derivatives, physicists would probably try to discard poles in alpha. It's just, I mean, it's actually not quite the same, but it's often much easier calculation.
And what you're suggesting, David?
Well, dimensional regularization.
Oh, yeah.
It's something a little bit
Yeah,
like dimensional regularization, but it's if you will get poles in the alpha, which you.
But I think this is more or less what it's doing, no?
Yeah.
Because it's discarding something which is not finite. No? I mean, it's
That's right.
discarding-
You are that's right.
Extracting a finite part. Right?
But there are more than one way to extract a finite part, and sometimes just discarding a pole is actually turns out to be the one that
It's
leads to the
the
simplest
funds
computations.
Pardon, these to the?
For physicists, it leads to the simplest computations, to just discard poles rather than to actually subtract off Taylor series and things like that. So, for example, to define convolution by 1 upon x to the alpha, when it starts to be non-integrable, you can subtract off, you can take your test functions and subtract off Taylor expansions to cancel the pole, or you can compute it for complex alpha and just throw away the pole after you've computed it.
I mean, here you mean delta, no? No.
Maybe I mean something else. I thought it was an alpha fractional derivative.
Yeah, I mean delta, you can think of that as alpha, it's not the same, so.
Yeah,
Alpha.
You alpha, yes, and alpha.
Yeah.
There might be poles in that if you go to complex values of alpha, which you can discard, and then you've done the same thing. Not quite, but similar thing to subtracting off the Taylor expansion.
Thank you for the suggestion.
I mean, that was what Gelfand was doing. You define x to the lambda as a meromorphic distribution.
Yes,
And
exactly.
then go to lambda negative.
Sounds interesting. Thank you.
Okay, well, no more questions?